This video explains how to work medium-level problems on the AC mesh equations tutorial in Circuit Tutor. As always, we have the option to view examples, but in the interest of time, I'm going to go straight to an exercise here. Okay, so at the medium level, we have something new, which is that we will have current sources present. And that means that we're going to have a current constraint equation is going to be necessary. So let's do that equation first. And basically, this current source is going to constrain this non-reference mesh current, which is I4. And so I4's value is going to be given by essentially the value of that source. So we put in I4 there. And then the value of the source is I1S. So we see that that's 2 angle 120 degrees amperes. But notice that I4 actually goes opposite to the direction of the I1S source. So we actually need a negative sign here. Or equivalently, we could change 120 degrees to be negative 60 degrees. That would also introduce a negative sign effectively, because remember that 1 angle 180 degrees is equivalent of -1 in polar notation. So we'll check that, and that is correct. Now let's write our SOT variable equations. We have a SOT voltage and a SOT current. So we'll select a SOT branch voltage. And again, this funny display here is just an artifact, unfortunately, of my video capture system. You won't see that in the actual game. Okay, so for V0, we see that that's a voltage across this negative J6 ohm capacitor. And there's one non-reference mesh current going through that, so we'll need this type of term. And basically that's going to be I3. And then the impedance would be the minus J6 ohms. But then we always want to check polarity, so we notice that I3 is going into the plus side of V0, which is indeed the passive sign convention that we'd like to be using to have a plus sign in the V equals IZ expression. So indeed this should be a plus sign in this case because of the polarity of I3 relative to the V0. So we'll check that. And then we also have a SOT branch current, I0, which is this current down through this voltage source. Now you might say, well, we don't know the current of a voltage source because it's whatever it needs to be, which is true. But in this case, because we're doing mesh analysis, it's simply going to be related to a non-reference mesh current, namely I1. So that's actually quite easy. So SOT branch current here, we'll say I0 is equal to 1 non-reference mesh current, which is I1, except that I0 actually goes opposite to the direction. I0 goes down here, whereas I1 is going to flow up. So that needs a minus sign there to be correct. And we'll check that, and that is correct. So now we have our SOT variable equations. So now we're going to do the KVL equations, which are the more complicated ones, usually. And we'll start out here with mesh 1. And we see that as we go around mesh 1, we're going to add the voltage drops, as always, using Kirchhoff's voltage law, which remember that's the basis for all of mesh analysis. So we're going to have 2 fixed values of voltage for the voltage sources. So we need 2 terms like this. And then the third term will be the voltage drop across a resistor with just 1 non-reference mesh current going through it. So that would be this type of term, and that must always sum to 0 by KVL. So let's start at the lower left corner and add voltage drops going in a clockwise direction. I like to go in the direction of the defined mesh current because that will make the terms for the passive elements have plus signs, at least for the mesh current that we're using here, the I1. So the first voltage drop would be across V1S, and that is in fact a voltage drop because we have the positive side going to the negative side. So that's just going to be the value of V1S, which as we see is 5 angle 0 degrees volts. So we enter 5 angle 0. And then going to the right, doesn't matter how many mesh currents go through this because it's just given by the value of the source. Now here it's actually a voltage rise because in going from left to right in our clockwise direction, we actually go from the negative side of V2S to its positive side. So now we need a negative sign there to indicate that. And then the value of V2S is 3 angle 120 degrees. So we just put that in here. Again, we cannot use the I2S symbol in here. That wouldn't be something you could even enter into these terms. And then finally, we have the voltage drop across the 2 ohm resistor as we come back to the starting point, and that's in a clockwise direction. And that'll be the passive sign convention. And only one non-reference current goes through that, which is I1, and then we just put in the 2 ohms, and that'll have a plus sign. So that's our first KVL equation. Now next we're going to do one for mesh 2, and there's only 2 elements in mesh 2, and each of them involves a difference in mesh currents, non-reference mesh currents. So we'll add those 2 together, and that will have to sum to 0. So let's start down here. We go across the 8 ohms. I2 goes in that direction, so it'll be I2 minus the current going the other way through the 8 ohm, which is I4. And that will multiply the 8 ohms. So the net current to the right, in other words, is I2 minus I4, if you want to think of it that way. And then as we go down to the J1, I2 goes down, so it's going to have the plus sign. And I3 actually goes up through the J1 element this way. And so that's going to have a minus sign. So it'll be minus I3, and then it'll be times the inductive impedance, which, as you remember, are positive imaginary numbers always. Okay, now for mesh 3, we're going to have an element with 2 mesh currents and then 2 elements with 1 mesh current. So we're going to have 1 term like this and 2 terms like that. Remember, we need a separate term for each element. And so again, starting lower left, the J1, we're going to have I3 minus I2 times that J1. And then we're going to have, going down through the 4 ohm, we just have the I3 times the 4 ohm by Ohm's law. Again, we're adding voltage drops going clockwise. And then finally going back to the left here, again, the sign of V naught here is absolutely irrelevant to what we're doing. We're just adding voltage drop, but it happens to be consistent, but it doesn't matter whether it is or not. It's still going to be the same. So we have I3, which is the only mesh current, non-reference mesh current through that element, and then that's times negative J6. And we check that, and that's correct. And that's meshes 1 to 3. Now we need to do mesh 4, but remember, mesh 4 has a problem because we have a current source, and the voltage drop across a current source is whatever it needs to be. So in fact, we cannot write an equation for a KVL equation for that, but that's okay because we already have a current constraint equation for that mesh. So we actually have enough equations for the number of unknowns as it is. So if you think about the mesh currents, we have 1, 2, 3, 4, and we have 1, 2, 3, 4 equations involving those 4 mesh currents. So that's actually all we need. And then the sought variable equations, well, there's 2 additional equations and 2 additional unknowns. So everything is fine. And now we just click no more equations. And we do have the option of viewing a more detailed explanation, which I will skip now in the interest of time. Thank you.